So the question is Leetcode number 129. This is the sum root to leaf numbers. Okay, so like I simply to describe you in briefly. So there's a tree given there. Okay, it contains digits from 0 to 9 there, and like each node contains digit, it's ranging from 0 to 9. We have to simply return all of the total sum of all root to leaf numbers. Okay, and these are fit in 32-bit integer. So like we have to what's the given this test case, there's this path, so it contains 1. When it goes to 2 it become 1 2, it goes to 3 it 1 3. So what is the total sum? This is the 1 2 and 1 3 mean 12 and 13, it gives total sum is 25. Let's say there's a one path is this 495, there's a 1 491, there's a 40, total sum is 495 plus 491 plus 40. So what we simply was simply given in this, we have to sum all of the numbers. And what are these numbers? These are simply the all sum of in correspondingly there is the path. Okay, so like let's say what the brute intuition over the for this, since there's a each number a root to leaf path, it forms a number like there's a 491, so it become number 491. Okay, so what is the brute force? We simply generate all of the root to leaf path, and we have to convert each path into a number and simply add them. Okay, so we store these the path digits in a vector, and when we reach at the leaf node we simply build a number. Like let's say I write the code and then I explain it by using a dry run. So let's say we have to make one our vector for storing this, and we have to call for this, we have to solve. Okay, so this is the root there, this is a vector v, and after we have to return our, and let's say this we have to define the globally int answer equal to 0. Actually there's a one it is not working, so I use this also. Okay, so to return this answer, and now there's the definition of this. So this is the void of the solve function there, and there's the tree node, and there's a, let's say to define this as a node, and there is a definition of this vector v. Okay, now there's base case here. So what it is, if node wait a second, this equal null, it simply return. Okay, since this is a code, so we don't have to write anything other, and in each case we have to use push back of nodes value. Okay, and for we have to check for the when we have to reach at the leaf node, since this is a leaf node here. So if I'm using this part, okay, if the nodes left and nodes right is equal to leaf, so let's say this is in sum equal to 0. Okay, now for I equal to now the sum become so here okay, like wait a second, first of all I write the code and after it I explain it to you. Okay, similarly call for the left part, so this is for left part. Similarly call for the right part. Okay, and since after returning we have to, the crucial step is to pop back this also. Okay, let's say I write this at before backtracking. Okay, so this is the final code there. This is the brute force here. So we have to try running this part. So I think you need you so let's say there. Okay, so first of all I've simply used the one there's a, see what are the parameters I passed there. We simply use the one our storing vector there, and in storing vector in our v vector, first of all I store part 4 only. Okay, now in vector when it goes to its 9, so here it v become or v consist 4 comma 9 there. Okay, when it goes to its left part, so v become, so it contains 4 comma 9 comma or 5 there. Okay, so since we have to reach at leaf node, now what I have to do here, we simply add up this number. So first of all we make this number as an equivalent number. So how we do this part, so I think you know this very well, like whenever we have to write 1 2 and 3 there, like these are given in the separated part there in an array, and we have to make this as equivalent as equal to 1 into 2 into 3. So what we simply do here, let's say there's a this is a part 3 here. First we initial let's say okay, so how we do, like how we summing of this array at the ending of the sub array, we initialize some vector here, and after it we have to sum into 10 plus v of I, sum into 10 plus v of I. So what it means, so initial our sum is equal to 3, so sum is equal to 3 here. Okay, now when it goes to I equal to 1 there, so sum becomes sum into 10. So what it means, so sum is equal to sum into 3, sum into 10 means 30, and plus its node value means v of I, so 30 plus 2 means it become 32 here, so it becomes there 32. Okay, and when it goes to I equal to 2 here, so its sum into 10 means 320 plus 1, 320 plus 1 means 321. Okay, so similarly like I explain it in reciprocal way, it initializes from this one part and it goes to this 3, so it become 1, then 1 plus 2, then 12, then it become 1 2 3. So like this is the how this is the calculation of this number here. So what we do here, simply this 4 call for its left, this call for its left, and since this is a leaf node, now what are the number storing in this till there, we have to make this as equivalent number. So what it become 495, we simply add up this number. Let's say this is our final answer vector, we define it as globally, and we have to add this sum plus equal to the left part. And now during returning, like let's say we have to incorporate this in our answer. Now during returning, since this is passed by reference, so we have to do the backtracking part here. So we have to explicitly eliminate or we can say explicitly pop up this 5 here, so it become 4 comma 9. So that's why we have to do this part also. Okay, so this is simply how's the definition of this. This is the base case. Add up this number of our vector, call for the left part, call for the right part, do the backtracking step here, and check if there is a leaf node we check we write the equivalent number of this part and add up this in our some answer vector. So what's the time complexity here? So let's okay, so there's a time complexity is since let's say here, okay, since for each of the leaf we rebuild the number using the path here. So since each node is visiting once time and we have to copy this current path in our final vector, copy this current path, so means our resultant time complexity become this, and similarly space complexity become the O of H here. Okay, now this is an cross h, or in the worst condition it's become n squared, so it means it is not the brute force, since it is acceptable because the constraint is very small. But let's see if we are able to reach to more optimized way in this. So how to go? Okay, so you have to notice something here, like when the, let's say we have the our forming element here. So what we do here, when we for this we have to add up this 4,9, then with this 4,9 4,5. If what we so instead of storing the digits and rebuilding, we can carry on this number while traversing. Mean what I have to what I'm taking what I have to explaining here, what we do in our brute force, we during traversing we store this in our vector, and now store this, calculate this is as equivalent number and store in our final vector, final answer there. And similarly do for this path, similarly do for this path. So there's a n one time complexity there, but there's an extra time complexity of again traversing this and storing this in number. So skipping this part, what we simply do, we simply pass our equivalent number here. And how we do this equivalent part this is by using this sum into 10 plus v of I. So what I'm trying to say, during instead of storing, we can carry let's say we can carry what we carry, there's a current path here, and what is become, there's a current path into 10, and it becomes the node value. Okay, so we can carry this during traversing, so it skips the extra traversing during the leaf node. Okay, so this avoids recomputation, so it skips our most of the unusual the unnecessary time. So this is the more optimal way. So how to do this? So what it meaning, while doing the DFS part, we have to maintain a running number. So this is our running number, this is goes from here to here to here. Okay, so when we reach a leaf node, so this running number, it already represents the full root to leaf number. Okay, so we simply add this our answer. So we here no need to store any path or no need to rebuild the numbers. This keeps a traversal of simple and it avoids our extra work there. Okay, so the code for this brute okay, so now we don't need this extra vector here. Okay, let's say this make this as a clean code here. So here we have to pass this running sum, or we can say the current sum here. Okay, and let's say this is return here, so this it become return 0 there. And how's the definition of this? First of all, since it gives us a number as here, so there's a return time become int, and this is now this is int sum equal to 0. Okay, and this is the base case of here. Now this is here what we do here, wait a second. Okay, sum is equal to sum into 10 here plus nodes value here. Okay, let's minimize this part, maybe it is used in further part. Okay, So during each of the node, we firstly update our the number. This is our running sum. This is our running number that goes from the top to bottom. Okay, and there's no need for this since this is a return type. So what we do, this is, let's say we can rename it as a DFS or surf, but there's a left comma sum plus sol, there's a node, there's a right comma sum here. Okay, and now it does not need we simply return our sum value here. So now I'm explaining this using dry run here. Okay, so again call for this function also, this again for this test case already. So let's see. Okay, like ignore this part because if I have to erase this, the image also erasing there. So let's skipping this part here. Okay, so now, so what's in this optimal way there, we simply pass our the node there, and there's the running somewhere. So here our sum become, first of all our sum is equal to 4 there. Okay, now it call for its left. So what is the sum call for here, and we have to update this path, and it return for its left part and from its right part. Okay, so like it call for its left, it call for its left. Okay, so when it reach at the leaf node, so there's the termination point. When it reach its leaf point, and it simply return the sum here. Okay, so let's, okay, so there's a sum 4. When it calls for its left, the sum become, it become 4 9. How is become 4 9? 4 into 10 plus 9 means 49. Okay, now when it calls to its left, so it become sum comma 4 9 5. Okay, okay, so since this is a leaf node, so what the condition, if leaf node, so it doesn't go to its left part or right part, means it return this sum value here. So that's why I write this, it return the sum value here. So it return the 4 9 or 5 there. This, you know, like 4 9 5 there. Now it go to its right part. Okay, here our sum become 4 9 and the 1 here. Okay, again this is the leaf node here, so it also return this sum part here. So here it becomes sum 4 9 1 there, and there's a 4 9 5 there. Now for this node, it have to sum this part 4 9 5 plus 4 9 1. So it become 4 9 5 plus 4 9 1, and it return this value to its node here. So there's a this step, there's a return from the left part, and there's a return from the right part. So there's a 4 9 5 from here, and it return 4 9 1 from here, and what it return to its left part, its upper 4 9 5 plus 4 9 1, that is our 9 8 6 there. Okay, now since it travels from its left subtree, now it go to its right, so it calls for its right, DFS call for it. So here the sum is equal to since here sum is equal to 4, so what is the sum here, it become the 4 comma 0. Now since this is a leaf node, means it have to return this, so it return this okay, so what it call here, so it return here 4 0. Okay, 4 0. Now for this node, since it gains from it from the left, and this gains it from the right, so at the finally it return here 4 9 plus 5 plus 4 9 1 from the left, and the 4 0 from right. That is our the desired value. So that's the code from here. Now so simply what's the time complexity here, since each of the node is visited once there, so time complexity is simply this is, and the what's the time space complexity is here, it's nothing but the height of the tree, so of h there. Okay, so this is the question here.